This lesson, we're going to learn how to do addition and subtraction of vectors. The vector addition of two vectors A and B is called the sum or resultant of the two vectors, and it's often denoted by vector R. If the vectors given are geometric vectors, then we follow the tail to tip rule. That means we place the next vector with its tail on the head, which is the tip of the previous vector. Then the resultant is a vector with the tail at the tail of the first vector and the head at the head of the last vector. If the given vectors are algebraic vectors, which means we know the location of the head as an order pair, then the resultant vectors can be found by adding the x components together and the y components together. Now, let's do some examples of addition of geometric vectors and the algebraic vectors. Example 1. Use the diagram to compute the followings, both geometrically and algebraically. So let's look at the diagram on the right. Given the vectors A, B, C, D, we're going to find the following resultant. Part A, we want to find the resultant that is the result of vector A plus vector B minus C. So first, let's copy down vector A, which is 3 squares to the right, and we're going to add a vector B. When we add the vector B, make sure we put the tail to the head of the vector A. So that's our vector B, going 2 units to the right and 3 units up. And then we want to find negative C. In vector addition, there's no subtraction. So minus vector C really means adding an opposite of vector C. So let's take a look. If we switch the tail and the head, it becomes negative C. And we're going to put the tail to the head of the green vector B. Now we can find our resultant from the tail of the vector A to the head of the vector negative C. So this red vector, which is our resultant of vector A plus B minus C. Part B, we want to find a vector R that is A minus bracket B minus C. Since there's a bracket, so we have to figure out what's vector B minus vector C first. So let's do a vector B first on the diagram, and we draw a vector negative C. We're going to add the knob to create a brown vector. Vector B minus vector C. Then we're going to figure out what's vector R now. So first we draw a vector A, and we draw an opposite vector of the brown vector B minus C. So we just switch the tail and the head. So we're going to have this. And then we can have our resultant from connecting the tail to the head. And the red vector R is vector A minus bracket vector B minus vector C. Part C, we want to find the resultant R is vector D plus bracket vector B plus vector C. So once again, since there's a bracket, so we have to figure out what the bracket is. So first thing we do is draw a vector B, and we draw a vector C by connecting the tip to tail. And from the very beginning tail to the very ending head, that's our vector B plus C. Next, we're going to draw a vector D now, and we're going to draw the purple one, which is B plus C, and from the very beginning tail to the very ending head, that's our resultant, R. Now, let's try to do all those questions again, but this time we're going to do it algebraically. So that means we have to find all the algebraic vectors for vector A, B, C, D. So how do we do this? We have to pretend the tail is at the origin, and we're going to find the location of the head. So as you can see, vector A is actually having an x-coordinate of 3 and y-coordinate of 0. So we say vector A, 3, 0. Likewise, if the vector B's tail is at the origin, then the head is going to have the coordinate of 2, 3. So we say vector B is 2, 3. Similarly, we say vector C is 0 and negative 2, and vector D will be negative 3 and 2. Now, we are ready to do part A. So vector r equals vector a plus vector b minus vector c. But since there's no subtraction in vectors, so we have to multiply the negative into the coordinates for vector c. So we have -1 times by 0, which is a 0, and -1 times by a -2, which is a 2. And in order to find the resultant, we're going to add all the x coordinate up together. So 3 plus 2 plus 0, so it's going to be 5. And we're going to add all the y components up together too. So 0 plus 3 plus 2 will also be 5. So now our resultant r will be at 5, 5. That's verified with our geometric vectors. So if the tail of the resultant is at the origin, then the head will be having the x value of 1, 2, 3, 4, 5, and the y value of 1, 2, 3, 4, 5. So as you can see, it doesn't really matter how we add the vectors, geometrically or algebraically, we will have the same result. Part B, same thing again. We have to figure out what's vector b minus c first. So we put a bracket around it. So we're going to do vector b minus vector c first. And then we're going to have 3, 0 minus 2, 5, which we're going to have 1 and -5. Once again, if the tail of the vector r is at the origin, then we can see the location of the head is at x value of 1 and y value of -1, -2, -3, -4, -5. Part C, we're finding the resultant r equals vector d plus the bracket vector b plus vector c. So we have to figure out what's inside the bracket first. So we do x plus x, which is 2, and then we do 3 plus -2, which is a 1. So we get 2, 1. And then we will do x plus x again, which is -1, and y plus y again, it will become a 3. So it's going to be -1 and 3. So that's a verifier with the geometric vectors again. So if the tail of the resultant is at the origin, the head will be having an x value of -1 and 3 units up. So -1 and 3. Example 2, a cube is constructed from using 3 vectors, vector A, vector B, vector C, as shown in the diagram. Express the following in terms of those 3 vectors. Part A, we want to find vector AF. That means we want to go from point A to point F. Let's pretend this pink vector AF is on constructions, so I cannot use this line to go from point A to point F. So what is the different routing that I can take? So one of the routing I can use is from point A to point B, and from point B to point F. And we can write vector AB using little a, and we can write vector BF using little c, because BF and vector AE, they are equal vectors. So therefore, we say vector AF equals A plus C. Part B, we want to find vector CF. So vector CF. So once again, I can use the routing vector CB plus vector BF, which is equivalent to negative little vector B. Because B is this way, that means CB will be opposite of vector B. And this vector BF is actually our little vector C. So vector CF can be written as negative little b plus little c. Part C, we want to find vector AG. So once again, we cannot use this line. So we're going to choose a different routing. So we're going to do this. Vector AB plus vector BC plus vector CG, which is equivalent to vector A plus vector B plus vector C. Part D, we want to find vector B to H. So once again, we cannot use this blue line. We have to choose a different routing. So I'm going to choose BC to CG to GH, which is equivalent to vector B plus vector C minus vector A. So we write out negative A plus B plus C. Example 3, given the magnitude of 2 vectors, which is 8 and 6, and the angle between those two vectors is 120 degrees. Find the magnitude and the direction of the resultant r, which is vector A plus vector B. First, let's draw the vector A, which is 8 units long, and it is always easier if we draw the first vector on the horizontal line. Next, because I know the angle between those two vectors is 120s, and the angle between two vectors is always tail to tail, so I know my vector B is pointing this way, and with 120 degrees between them. Now, we are ready to find our resultant, vector A plus vector B. First, let's draw vector A again. Next, since we're adding the vector B onto vector A, so move the tail of the B to the tip of the A. So that's our vector B. Then, let's find our resultant. Our resultant will be from the very beginning tail to the very ending head. So, our resultant R will be right here. And that's the vector we want to find. Let's label all the values that we know on the diagram. So first, we know the magnitude of A is 8. And we know magnitude of vector B is 6. And we know the angle between the tail of the vector A and B is 120. That means we know this angle is going to be 60 degrees. And since we know 3 sides, 1 angle, we can use cosine law to find the magnitude of the vector R. So we know vector R magnitude squared equals A squared plus 6 squared minus 2 times by 8 times by 6 times by cosine 60. And we're going to have R squared equals to 52, take the square root on both sides, so we know magnitude of vector R equals square root of 52, which can be reduced down to 2 square root of 13. Now we have the magnitude. The next one, we're going to find the direction of the vector R. So since the tail of the vector R is connecting to the tail of the vector A, so this angle is the angle we want to find. So let's call this angle theta. Since in this triangle, the only angle we know is 60 degrees, which is acute angle, that means theta could be an obtuse angle. Therefore, we do not want to use sine law to find this angle. We want to use cosine law to find this angle, just in case if theta is going to be obtuse angle. As you know, sine law can never be used to find an angle that is obtuse angle. According to the cosine law, the side that is opposite to the angle that we need to find must be isolated on the left-hand side of the cosine law equation. So therefore, we have this line here. And the next thing is we have to isolate for cosine theta. So we subtract those two terms on both sides of the equation, and we're going to divide it by -2 and divide it by 8 and divide it by the magnitude of the vector R. You are going to have cosine theta equals 5 square root of 13 divided by 26. By taking the cos inverse, we will find theta as approximately 46.10 degrees. Therefore, vector R, which is vector A plus vector B, is the magnitude 2 square root of 13, and with the direction in the square bracket, 46.10 degrees to vector A. Example number 4. The given information is going to be the same thing as example number 3. Magnitude of the A is 8, magnitude of the B is 6, the angle between them is 120 degrees, but this time we are finding the resultant of vector A minus vector B. Once again, we draw the first vector, vector A, on the horizontal line, and let's make 120 degrees over there to draw a vector B, and we label 120 degrees. Then, let's do the diagram again by doing A minus B. So once again, we draw the vector A, copy it, and we know vector B originally is here, making 120 degrees here. But right now, we are doing minus vector B. That really means we are adding an opposite vector B. That means we switch the tail and the head and move the tail to the head of the vector A. So we're going to have this. Then we can find our resultant vectors by connecting the most original tail to the most ending head. That's our resultant R. Moreover, because vector b and vector negative b, they are parallel lines. So as you can see, those two angles are called alternate angles. So if we know this angle is 120 degrees, that means this angle is going to be 120 degrees. That's the label, other information that we know. We know the magnitude of vector A is actually 8, so we write down 8. And we know the magnitude of vector B is 6, but negative B is only an opposite vector. They will have the same magnitude. So we know magnitude of vector negative B is going to be 6 as well. Now that we have 3 sides of one angle, then we can use cosine law again. So we get magnitude of r squared equals a squared plus 6 squared minus 2 times by 8 times by 6 cosine 120 degrees. Once again, remember the angle and the side must be opposite. And we can simplify to magnitude of r squared equals 148, which means we can take the square root on both sides to find the magnitude of the vector r is square root of 148, which can be reduced to 2 square root of 37. Next, we have to find the direction angle. So we know the tail of the vector r is actually connecting to the tail of the vector a. So this angle is the one we want to find. That's called alpha. Because we already have an obtuse angle in the triangle, that means alpha will not be an obtuse angle. Therefore, it is safe to use sine law to find the alpha here. So we have sine alpha equals 6 over sine 120 over the magnitude of the vector r, which is 2 square root of 37. Then we're going to times by 6 on both sides to isolate sine alpha. Then we're going to do the sine inverse to find alpha. And alpha is approximately 25.28 degrees. Therefore, we say vector r is vector a minus vector b equals to the magnitude, which is 2 square root of 37, and with the direction angle, 25.28 degrees with vector A. Example number 5, we would like to do analysis of all the different cases when you're adding two vectors, A and B. Let's look at the first case. If the angle between vector A and B is 0 degrees, then we have a vector A and vector B. When you put those two tails together, the angle between them will be 0. Then when we add the vectors, you're going to have the resultant of the red one here. And when you subtract the vectors, when you do A plus negative B, you're going to have the short blue vector here. So we know when the angle between the two vectors is 0 degrees, the resultant of A plus B is definitely longer than the resultant of A minus B. Case 2. If the angle between the vector A and B is an acute angle, then your diagram will be very similar to this. That means when we are adding the vectors A and B, then you are going to have the red resultant here. And when we have the vectors A minus B, then your resultant will be the blue one here. And as you can see here again, the red resultant is longer than the blue resultant. Therefore, we know as long as the angle is between 0 and 90, the resultant of A plus B will be longer than the resultant of A minus B. Case 3. When the angle is actually 90 degrees between vector A and B, then you will see when you do vector A plus B and when you do vector A minus B, the resultant will have the same magnitude. Case 4. When the angle between the vectors are actually obtuse angle, that means your diagram will be very similar to this. This time you can see the resultant, the red one, of the vectors A plus B will be shorter than the resultant of the vector A minus B. Case 5. When the angle between the two vectors is 180 degrees, that means vector A and vector B are pointing in the opposite direction. So you can see vector A plus B, the resultant will be shorter than vector A minus B. So therefore, we can do the following conclusion. The magnitude of the resultant of vector A plus vector B is greater than the magnitude of the resultant of vector A minus vector B when the angle theta is 0 degree or an acute angle. Second, the magnitude of the resultant of the vector A plus vector B is equal to the magnitude of the resultant of the vector A minus vector B when the angle is 90 degrees. Third, when the magnitude of the resultant of the vector A plus vector B is less than the magnitude of the resultant of the vector A minus vector B, when the angle is 180 degrees or an obtuse angle.